Okay, yeah, thanks for coming. This is Evan Hill. He works on solving a lot of thorny problems with LIGO's controls and their projections for science targets for future detectors, and also has a couple of tabletop experiments that he's going to tell us about today. Yeah, go ahead.
Thanks. Yeah. Thanks for having me. It's really good I've never been here before. It's really nice to be here. It's really nice to see everybody's labs. But yeah, so this talk is going to be mostly about dark matter, although a lot of what I do is really more LIGO stuff. It'll be about a dark matter experiment that is heavily inspired by LIGO, and so along the way, I'm going to end up talking about a lot of LIGO technologies. So there we go. So I took one of these dark sort of attempts at a dark matter overview from a recent-ish review in Nature that just orders dark matter candidates by their mass from the lowest scale, 10 to the minus, maybe 10 to the minus 22 EV, all the way up to very, very heavy objects like black holes. I like this particular one because it sort of calls out at least some of the experimental techniques that you can use in different mass scales. For this talk, I'm going to be talking exclusively about wave-like dark matter, so sub-EV. Actually, I'll spend most of the time talking below a micro EV. In particular, I'll stick to talking about photon-coupled axions or photon-coupled axion-like particles. Most of you probably know this, right? There's an interaction Lagrangian between the axion field A and then an electromagnetic field with a coupling constant G gamma gamma. That interaction Lagrangian modifies Maxwell's equations, gives you a charge density term, and also gives you an effective current. And just for nomenclature, I'll try to distinguish between axions like the QCD axion and an axion-like particles that don't necessarily need to be the QCD axion, but I might slip up. I took this particular exclusion plot from the recent recent-ish SNOMAS process from 2021. So again, focusing on those are fun.
You reflex off the screen.
All right, then I'm okay. So there's obviously a lot of experimental constraints on this, but what I want to highlight, so there's obviously the cast result that's been there for a while at sort of 10 to the minus 10 per GeV. There are a number of astrophysical constraints that sort of, including supernova constraints that are a little bit more strict, sort of below a micro EV. And then obviously some things that are new from maybe 10 years ago, what would not have appeared on this plot 10 years ago. Obviously the haloscopes have pushed down further in the space of G and also have covered more mass, and they're now hitting some of the benchmark models for the expected coupling for the QCD axion. There are some experiments that are up that they maybe just barely exceed the cast bound, but they weren't there 10 years ago. So there's this particular thing called Abracadabra and this thing called Shaft. Those are both toroidal magnet experiments. And then the other thing to point out here is that probably what did not appear 10 years ago was this exclusion based on black hole spins, black hole superradiance. I will talk about that in a few slides. But what is not on this plot is actually the kind of apparatus that I want to talk about, which is has to do with optical cavity effects that sort of people have been exploring in the past few years. Right, so maybe not every single one of those previous experiments on that plot, but most of them are exploiting one of a few phenomena for how axions or ALPS might produce an observable effect. So obviously, conversion to or from photons in a strong B field, right? That's what haloscopes are looking for, the magnet searches, regeneration experiments, helioscopes, and a lot of the astrophysical bounds, one way or another, are also looking for that. The effect that, for the experiments that I'm going to talk about, the effect that I want to talk about is this optical activity effect. So that's what motivates these polarimetry searches and also searches with superconducting RF cavities. And then there are also astrophysical constraints that use this effect like CMB bounds, but those are for very small masses. And then the one that I mentioned from the previous slide is there is this super radiance effect, which I'm going to get to a little bit later. So the optical activity effect is the following. If you take Maxwell's equations and you add in the axion terms, and then you solve them for a plane wave geometry of an E&M field, you find out that the dispersion relation for a plane wave is modified in this particular way. So rather than k squared minus omega squared being 0, you get this term that is proportional to the coupling constant and the derivative of the axion field. So what that means is, since the axion field, the ALP field, we think oscillates at the constant frequency of the axion, there is a time varying dispersion as a plane wave travels through an ALP field. You can also think of it in a modal picture. So in a modal picture, you start with a particular linear polarized plane wave at omega naught. Say it's in the p polarization. Then as it travels through an axion cloud or an ALP cloud, it develops upper and lower phase modulated sidebands at the optical frequency plus or minus omega axion. So this is a sort of situation in which if you work a lot with optical cavities, you get the idea that this is maybe an effect that, even though it's very small, as with many of the proposed axion signatures, it's something that could be cavity enhanced and is potentially observable. So because these have different frequencies, what that means is you need to find a cavity probably that is birefringent if you're looking for large frequency separation. Okay, so it's an effect that could be looked for in optical cavities. So one question is it possible that there's already an optical cavity that's taken data that might actually show this effect? So in other words, can you see it in LIGO? Can you see it in the arm cavities? Now, the LIGO arm cavities are not birefringent, but that's okay, because you might still, if omega A is much, much smaller than the bandwidth of the LIGO arm cavities, you might still see it because both polarizations are still resonant. So the answer to this question is yes, with some caveats. So the LIGO arm cavities are just two mirror cavities. There's an input test mass and end test mass. In a two mirror cavity, if you have a polarization rotation of the light field, when it reflects off the mirror, the reflection operation reverses the sign of the polarization shift. So what that means is every time the plane wave or the light traverses the arm cavity, picks up a polarization shift. When it reflects, that polarization shifting cancels out. At least so long as the light travel time is smaller than at least so long as the axion oscillation period is smaller than the light travel time down the arm cavity. So in the LIGO arm cavity, there's no actual cavity enhancement of the signal. There's obviously an enhancement of the pump, but not of the signal. So there's a sensitivity penalty from that. And then just generally for any optical cavity that has a certain length L or a certain round trip time, if you look for effects that happen faster than the round trip time of the optical cavity, you get averaging away of the signal because it tends to oscillate back and forth by the time it actually completes a round trip cycle. So in LIGO, that frequency is 37 kilohertz. So if you can convert that back into an axion mass, that's something like 1 10 to the minus 10 eV. So you expect there to be more or less a sensitivity penalty if you're trying to use LIGO above that mass. And then the other thing is that LIGO is currently configured is not actually set up to look for polarization effects. So you can't just go back and look at past data. You would have to install new optics, which is not hard. Installing new optics is not hard. The part that is hard is probably beating down the technical noise. And so you expect that you install new optics. It's not going to be shot noise limited out of the box. You're probably going to have some laser frequency noise or some other kind of polarization drift or something that requires a lot of mitigation to bring down the shot noise limit, maybe. So nonetheless, when colleagues in Tokyo made these projections for LIGO and for a futuristic 10 times longer LIGO, which is called the Explorer, and for a futuristic space mission, which is called the SIGO. And they made these projections using just the shot noise limit. And they assumed shot noise limited performance down to what is probably in interferometry is considered sort of low frequencies, so less than a hertz. Nonetheless, this is the answer that you get. If you installed some extra optics in LIGO, you would get to a GA gamma gamma of something like 10 to the minus 12 per GeV over a decade or a few decades in mass. And then sort of up above 10 to the minus 10 EV, you start getting a penalty. There are a couple of discrete frequencies where the effect is enhanced, but those are not really tunable. Those are just sort of accidents of the fact that you picked a certain arm length for LIGO. Sort of what is hinted at it by this plot is that there is this dashed thing that says ring cavity, which is their projection for how you might make a modified optical cavity that actually doesn't have this cancellation effect of the signal. It actually fully exploits resonance of the pump and resonance of the signal. So the way that works is rather than having 2 mirrors, you have 4. Again, you want to have a long cavity, so you want to have a long travel time over which the polarization state of the light inside the cavity can be rotated by the axion. But you have two reflections on each end, basically, and that, if you perform the reflection operation twice, you preserve the buildup of the polarization rotation. And so you inject at omega naught, the cavity enhances the pump at omega naught in the p polarization. You then get this generation and resonant enhancement of the signal at omega naught. Here I've chosen plus omega A. You could also imagine tuning the cavity to give you omega naught minus omega A. You can't generally enhance both at the same time. That happens in the S polarization. And then on the output, you would extract some of the pump, extract some of the signal. You would project them onto the same polarization state. And then you would attempt to read out a beat note at the Compton frequency of the axion of the alpha. And then there's just a simple relation. If you're looking for an alpha at a particular omega A and you have a cavity of length L, there's a certain radians of phase shift that you should try to hit for your birefringence. Yes.
If they're coming out P and S, how do you get a P?
The simplest thing to do, I suppose, is that you just use a polarizing beam splitter at sort of 45 degrees relative to each of them. You throw away half the light that way, but if the factor 2 is important, you could sort of get some optics to recover it. But you just project off sort of on an axis that's intermediate between the two of them. Yeah, so you can ask, what's the sensitivity scaling? So assume you're shot noise limited. That's the first place to start when you make these analyses usually. So if you compute the amplitude signal to noise ratio, so ultimately what is proportional to the limit or the sensitivity to which you could probe GA gamma gamma, that signal to noise ratio scales like the square root of the pump power, scales like the cavity finesse, so the circulating power divided by the power loss, Q factor. Scales with the cavity length, again, assuming that you're looking for ALPS whose period is shorter than the round trip time, or longer than the round trip time of the cavity. And then there is this usual T to the 1/4 scaling for integration time. It's very unfavorable scaling for integration time. So then you might ask, how do you actually allocate the experiment time? So you're assuming that you run for a year or you run for 5 years. So one option is to just do a narrow band search, right? So you keep the birefringence fixed. Could be fixed at 0 radians, could be fixed at some fraction of the free spectral range of the cavity. And that allows you to search for axions or for ALPS at omega A plus or minus the bandwidth of the cavity, which is just C by L times spin S. Or you can attempt to scan search. So one of the nice things about if you had a tunably birefringent cavity is that you would be able to, with a single cavity without changing the length, potentially without swapping out optics, you would be able to scan for omega A of 0. Again, it requires you to have very good sensitivity at DC, which is often very difficult, but omega A at some very small frequency up to an omega A of something like C by L. And again, if the total amount of experiment time is fixed, you're spending less time at each dwell point. But that's sort of the trade-off. So how do you tune? Right. So the very first sort of impulse that you might have with an optical cavity is to say, well, if you want to make it birefringent, you might put a birefringent material inside the cavity. That is okay if you were doing a low finesse experiment, you weren't too concerned with losses, you weren't too concerned with power absorption. In practice, for really high finesse optical cavities and for really high power optical cavities, placing anything inside the optical cavity is sort of incompatible with high finesse, high power operation. There has to be something else. Things that people have proposed are you could couple to a secondary cavity. So you make one of the main cavity mirrors partially transmissive, and then behind it, you have a secondary cavity. And the phase response of that cavity can be tuned, and you can change the polarization, the relative polarization phase shift that way. That could work if you can control the losses in that sense, in that second cavity really well. So it's something that would have to be proved on the tabletop. You could imagine having dispersive coatings. So you tune by wavelength. Or you can imagine tuning by angle of incidence, right? So you keep the laser wavelength fixed, but just generically with the kind of mirror coatings that you use for interferometry, they tend to have a dependence on the angle of incidence as you, the polarization phase shift depends on the angle of incidence. So we at MIT put together a prototype of one of these experiments. We picked the angle of incidence strategy mainly because it's simpler than anything else, and also because, again, just generically, if you take an optic that you already have and you run it off axis, you just get a phase shift between P and S, and it changes as you change the angle of incidence. So what's going on here is we had about a 1 watt laser, 1064 nanometer M-Pro. We phase modulate the light. We resonate the light inside the cavity in the pump polarization. And then we have a photodiode and reflection that collects the light reflected from the cavity and also these phase modulated sidebands. You can do a Pound-Druver-Hall technique to get an error signal from that. So that's how we lock the laser to the cavity. So the laser is stabilized to the cavity. We then have 2 high reflectors, which are both birefringent. Actually, all 4 of these optics in this case were birefringent. And then sort of as I showed on the previous diagram, any ALP field that passes through the cavity is expected to generate S-polarized sidebands that are resonantly enhanced. And then a little bit of the light leaks out of the output. And then I didn't draw the polarization projection optics here, but they are there, and we have an RF photodiode that we demodulate with our synthesizer, and then we digitize the demodulated signal, the demodulated data, and then we search that data for ALPs. Because this was a prototype, we didn't really have anything fancy to tune with. We just had the graduate students would open up the chamber, change the optical angle, realign everything, which is very tedious, but she did it for 5 data runs. We tuned the birefringence by hand, collected 5 data runs. This is a typical PSD of the demodulated beat note, calibrated back into watts squared per hertz. If you calibrate it back into phase, you get a sensitivity of a picoradian per root hertz at, again, sort of because of the cavity length that we had, the free spectral range was some tens of megahertz. And so naturally, with the birefringence that we have, you end up being able to search in sort of the tens of megahertz range. We didn't find any candidates with had an appropriate line width for the axion, for the ALP. We didn't have this asymmetrically thermally broadened result anywhere. And we also, we didn't with the prototype, we didn't end up probing new parameter space. So that's, again, it would just sort of for believability reasons, it's not like we didn't necessarily expect to find a thermally broadened candidate. Nonetheless, if we had found something, of course, there are many of the usual ways to try to distinguish that from a noise, or you can look for seasonal variation. And also we're talking about sort of 50 nano EV ALPs. And in that range, the de Broglie volume of the ALP is large enough that if there was another ALP detector running at the same time on Earth, looking at the same mass range, you would expect to have coincidence. So just a couple of ways that if we had really found something compelling, we could have tried to rule it out. So in terms of putting this in terms of mass and then G gamma gamma, this is the result that we had. So blue again is its cast and also the magnet experiments. Green is the astrophysical bounds, like I showed on slide 3. The bounds that we set were these. There's actually, again, there are 5 data taking runs in here, and just because the alignment was a little bit trial and error, you end up with this kind of sort of, we didn't smoothly fill in a contiguous sort of piece of mass space, but this is the result that we got. The dashed sort of cream colored line shows if we were able to smoothly scan the birefringence from 0 radians all the way to 2 pi radians, that is the amount of space. It's sort of the locus of curves that we'd be able to probe with the current apparatus that we have. So there is this red thing called LIDA. That is a similar apparatus from colleagues in Birmingham. I have a subsequent slide. I have some remarks on it. And then we made these projections for the future. So in this particular ADBC future, so ADBC, sorry, is the name of the MIT experiment to distinguish it from LIDA, and also there's a Japanese experiment called DANCE. So the ADBC future experiment is a scanned experiment assuming a longer baseline, 40 meters, more circulating pump power, a megawatt. And then we also, sort of a very simple model, tried to project what would happen if we swapped out a homodyne readout for a single photon readout. Like it's sort of considered sometimes for axion, for haloscope experiments. The other thing on this plot is this area that says black hole superradiance. This is probably a good time to talk about what that means and sort of how firm those bounds are. So black hole superradiance is the idea that if you have a spinning black hole, a Kerr black hole with a large amount of spin, then if you have a field mode, basically any field mode that penetrates into the ergosphere of the black hole, then there is a transfer of energy and angular momentum from the black hole to the wave mode. It's similar to a Penrose process. It's just a kinematic effect. It occurs even if there is no if G gamma gamma is 0, this effect should still occur. So you don't need a E&M coupling, you don't need nuclear coupling. In the particular case of a boson, a bosonic field, there are because the gravitational potential of the black hole is more or less Coulomb, you end up with bosonic modes that have this hydrogen-like bound structure to the black hole. So it's sometimes called a gravitational atom. You see that in the literature sometimes. But what that means is if you have a bosonic, some mode, even if its occupation number is initially 0, the spinning black hole will put energy into the mode, so it'll start to occupy the mode. And then because the mode is bound, the particles, the quanta in that mode don't leave. They actually they continue to be enhanced superradiantly by this process. And so you get an exponential growth of the cloud. There's then a couple things that happen once you have a sufficiently large cloud. So number one, the cloud starts radiating gravitational waves at twice the Compton frequency of the ALP. And the other thing that happens is you've extracted at that point enough momentum from the black hole that the black hole spins down and the superradiance process stops. So the canonical astrophysical scenario here is that you start with some black hole that is at a mass whose Schwarzschild radius is matched to the Compton wavelength of the axion or the ALP, because that's what you need to get an efficient superradiance process. The black hole it populates this cloud, the cloud spins down the black hole, the superradiance process stops, and then the boson cloud then slowly radiates away in gravitational waves over a period of millions of years. So with that picture in mind, there are a couple of observational astrophysical signatures that people are already looking for with LIGO data and also with X-ray observations of black holes. So one is that if you have a large enough census of black holes, if you can populate a plot that has black hole mass on the horizontal axis and black hole spin on the vertical axis, a signature that you would look for superradiance is you would look for an absence of highly spinning black holes in some particular mass range. That would be an indication that there is some process that is suppressing the ability of black holes at a certain mass to have a high spin. And there are fairly specific predictions for exactly what the shape of that suppression should be as a function of mass and spin. The other thing that you can look for is you can directly look for a long-lived gravitational wave signal from the superradiance. And the other thing that you can look for is, again, a gravitational wave signal, but in this case, you would look for a superposition of many, many black hole boson clouds radiating jointly, and we look for sort of a randomized stochastic signal from that. So there have already been some constraints placed in sort of, as I showed on the previous plot, sort of at the low kind of pico EV range based on LIGO observations. If with a full catalog of much deeper LIGO observations and also with LISA observations, there's a number of people, Vitor Cardoso, they make these projections for exactly how much mass range you could exclude for ALPS, and their sort of prediction is that with a sufficiently large catalog, you could exclude many, many orders of magnitudes, 10 to the minus 19 EV up to 10 to the minus 11 EV, as long as the ALPS are non-self-interacting. So there's a little bit of a loophole here in that if there is a strong enough self-interaction, you then have the opportunity for the boson cloud for the particles that are popped into the boson cloud to exit the boson cloud in some other way rather than just being exponentially driven up. So that's why, even though on this exclusion plot, we drew this band all the way up to infinity, but in the snowmass report, you'll see that exclusion kind of cuts off at a G gamma gamma of something like 10 to the minus 16 EV, because of this sort of potential for the boson cloud formation to be suppressed at strong couplings. It's an interesting sort of complement in the sense that you have these laboratory experiments that are attempting to probe G gamma gamma sort of from the top down, from larger couplings to smaller couplings, and then you have this complementary thing where you're able to exclude very, very small G gamma gammas using astrophysical observations. So that's superradiance. So I think I mentioned there are a couple of these laboratory ring cavity experiments for axions, each kind of trying a different thing or pushing on the technology in a little bit different way. So there's DANCE in Tokyo. I'll just say that the mass ranges probed here are essentially dictated by what optics people had available for to have a birefringent cavity. So they were looking at from 10 femto EV to 100 femto EV. They're pushing on the idea of maybe doing a wavelength tunability for their birefringence tuning rather than an angular or a cavity tunability. There's LIDA in Birmingham. It's the largest, it's 10 meters round trip. They tried to zero out their birefringence. They ended up with the birefringence that was sort of amounted to a Compton frequency of 400 kilohertz, which amounts to an axion, an ALP frequency, an ALP mass of 2 eV. They also got a very high circulating power, 120 kilowatts. And then there's the MIT experiment, ADBC. And we were going more towards demonstrating angle tunability and sort of how that all shook out. This is a picture of our 2-meter vacuum chamber that gives you a 4-meter round trip length. So that's the status of the prototypes. And what I want to spend more or less the rest of the talk talking about is the technology and sort of the fundamental limits for how far you could go with this kind of technology. So maybe, are there any questions on the first part? And again, because of my other life, I do a lot of LEGO work. A lot of what I'm going to talk about is essentially cribbing from what another very powerful optical cavity experiment has already encountered in terms of technological problems and fundamental limits, which is LEGO. So I've been harping on this birefringence a lot. How do you actually make a birefringent cavity? So for this, you have to look microscopically at how a laser mirror is made. There's a picture of a laser mirror on the right-hand side, and then a diagram of a laser mirror on the left-hand side. They're typically these sort of quarter wavelength stacks of often metal oxides deposited onto a substrate. And they alternate low index, high index, low index, high index. If you stack enough of them up, you can get very, very high reflectivities, greater than 99.99%. So again, if you operate these off axis, then you have different Fresnel conditions at the interfaces, so you get different reflectivities, and you get, in fact, different phase shifts between the two polarization modes, P and S. So you might ask, how do you make a birefringent coating that is tunable? This is, I would say, an open question. So you can just, in simulation, it's pretty easy to figure out how to make a birefringent coating. If that's the only parameter that you care about, you just, rather than having all the layers be quarter wavelength, you make one of them half wavelength. It's almost like having a little cavity in the coating itself. When you do that, you can get this this curve. I think I made this for 60 layers, one of which is a half wavelength layer. And then as a function of angle of incidence, you get this relatively sharp reflected phase difference between the two polarization modes. But then the question to ask is, how well can a coating company or a lab actually fabricate a coating like this? So in other words, what are the fabrication errors? 1% is generally doable. There are some research laboratories like Lincoln Labs that use feedback techniques to get that down to 0.1%. So if you add in a 0.1% systematic thickness error and you run, say, 100 realizations of this systematic thickness error, and maybe it's a bit too dim to see, but there is this bright sort of red curve that's the nominal, and then I've done 100 simulations of 0.1% systematic thickness errors, and you can see that the region in which the birefringence happens as a function of angle is moving around by something like half a degree. So there has to be a certain amount of realism in designing these coatings and a tolerance for fabrication errors and systematics. Otherwise, you spend $10,000 on coatings on some very fancy mirrors, and then they don't work the way that you want, and then the experiment's not going to work.
Why does it matter so much? Would you just change the?
Yeah, and yes, but if when a coating is this sensitive to angle of incidence errors, it also means it's likely to be sensitive to essentially any kind of optical path length fluctuations. So temperature sensitivity would be magnified. Noises like Brownian noise would be magnified. Yeah, so it is in this case, just from the perspective of correcting the angle of incidence. Yes, it is true that you can correct just by changing it, but this is sort of emblematic of the fact that it becomes more sensitive to everything. Yeah, so how would you actually make a rag reflector? What do you have to worry about? So fabrication systematics, internal electric field, right? So the proper way to analyze these coatings is really to solve for the electric field in every layer. And then the electric field in the coating has to be compatible with absorption, right? So you would have to actually have a coating that, suppose your overall cavity power was a megawatt, you would have to then work out how much electric field is in the coating, how much intensity that is it actually compatible with not melting the coating or, or some sort of horrible sort of photothermal effect. So along with that, you have to analyze the noise of the coating, the Brownian noise, the thermodynamic noise, and then sort of going on. Yeah, so angle control, temperature control, you have to make sure your coating is compatible with variations in angle and temperature. I guess the other point of why angle sensitivity is important, even though you can correct the DC value, is that if you made this apparatus suspended, then angle fluctuations in the suspension will just add a noise, and that's undesirable. The other thing you might ask is, okay, you can use metal oxide, which are amorphous, but why would you not just use a birefringent coating material? In fact, why would you not just make a two-mirror cavity where the P and the S modes just pick up a relative pi phase shift, and then you get rid of this double reflection problem? So it's an interesting question. The best studied example of thin film Bragg reflectors, at least for the optical cavities that I know about, is AlGas. AlGas is very promising for a number of reasons. It is still promising, people are still looking at it, but it turns out that AlGas has a number of very poorly understood polarization noises. So for a polarimetry experiment, it's a very risky candidate because it has this extra noise. So why am I harping on coding so much? It's because this is a problem that there are some special problems for polarimetry, but the performance of Bragg mirror coatings matters for a lot of different experiments. It matters for gravitational interferometers, it matters for dark matter searches, it matters for metrology applications like laser gyros, it matters for frequency references that people use in optical clocks. And in particular, the sensitivity problem that a lot of these experiments are coming up against right now is Brownian noise. Right, so Brownian noise, at least in the coating, in the thin film coating context, is that when you have internal degrees of freedom in the coating, like dislocations, anything that can produce friction on an atomic level, then the coating has a finite Q factor. And so you've coupled the coating's internal structure to a thermal bath, which is fluctuating. And so you get a Brownian noise. The mean squared phase shift as a function of frequency for Brownian noise in this context depends on temperature, depends inversely on frequency. And then sort of the two most important parameters, that it depends on the thickness of the coating, and then it also depends on the mechanical Q factor of the coating. If you can find a high Q factor coating material, it's very promising because it directly scales with the power spectrum of the Brownian noise. And sort of the overall problem with thin film coatings is, let's take silica tantalum as an example. Silica is the low index material, tantalum is the high index material. This is what is used in LIGO, it's used in atomic clock cavities, it's used all over the place. It has a Q factor of 10 to the 4, which as far as materials go, is kind of mediocre, right? We know that in bulk solids like fused silica, if you measured the Q factor of bulk fused silica, or you measured the Q factor of crystalline silicon or sapphire, Q factor is like 10 to the 8. So there's easily like 4 orders of magnitude of sort of degradation in Q factor for thin film coatings versus bulk materials. And I don't have an answer to that question. I don't think there's a fundamental reason why that has to be the case. Certainly a lot of coding research is going on to try to find lower loss, higher Q coating materials. But that's the current situation, is that you sort of are stuck with this relatively low Q factor for coatings. The other thing that is, I think, very important to understand for polarimetry and is usually not thought about in that much detail for optical cavities is that we typically think of Brownian noise as a displacement fluctuation of the coating surface. And so if you look at Brownian noise calculations for mirrors, the way the calculations were first done and the way the calculations are often still done is that you just compute the displacement fluctuation of the surface, You multiply that by the wave number, that gives you the reflected phase. And if that were the reality of how it worked, then you actually would not care for polarimetry. You would not care about Brownian noise at all, because P and S get the same phase shift on reflection. And because you're making a relative phase measurement between P and S polarization modes, the two should cancel. And it is not actually the case. This is known in the literature, but again, just because the formulas get very complicated, we don't usually think about it that much. But it is important for polarimetry. You have to actually solve for the field structure inside the coating to figure out what the reflected phase is. And when you do that, you find out that there's a sort of 10% contribution from this fact that the coating actually has an optical depth that has these multiple reflections. And so for polarimetry, it's reasonable to think that you might expect a cancellation of the Brownian noise by maybe a factor of 10 in amplitude, but it's not going to cancel completely. So all these projections that get made about having only shot noise and not needing to worry about coding Brownian noise probably need to be modified with a little bit more realism for what the Brownian noise of the coding is. Let's see. So the reason I'm harping on this is because all these experiments not only experience Brownian noise, but they're increasingly limited by it. This is a Gilla clock cavity displaying Brownian noise limit sort of at 0.1 hertz. This is a Caltech frequency reference cavity that's used for the frequency stabilization in LIGO. Brownian noise limited at 100 hertz. And then LIGO itself, all these plots are spectral density plots, so frequency on the horizontal axis and then noise on the vertical axis. LIGO itself, over the past few years, has been limited increasingly by Brownian noise of the mirror coatings on the test mass. So this was the situation in 2024. So at 100 hertz, there's this mix of coding Brownian noise, quantum noise, and then a small amount of unexplained noise, which is usually the case. There's always some additional noise that isn't understood yet. So like I said, because it affects so many different areas of research, there are a large number of experiments going on to look at new coding materials. But what I will say is that no one has found a coding material that's Brownian noise limited with a Q of 10 to the 8. Hasn't happened. People are going after factors of 2. That's kind of where the field of coding research is trying to eke out these factors of 2, which is very important for LIGO and very important for some clock experiments. But if you're still thinking in sort of orders of magnitude, where's the order of magnitude, gain going to happen? It might not be coatings, not the plan. So amorphous coatings, crystalline coatings, cryogenic specific coatings, metamaterials. There's another important one, limitations to cavity finesse. So there are certain cavity experiments, maybe in the microwave, where you can get these Q factors of 10 to 8 or something like that, very, very high Qs. In optical cavities, the finesse or the Q factor really never seen it exceed 10 to the 6 with finesse. And the reason for that is the following. So first of all, there's a small contribution from optical absorption. Silica tantalum mirror coatings absorb a little bit less than 1 ppm per mirror. And most of the finesse limitation is scatter. And most of the finesse limitation is, it's not necessarily a particular surface error, other than it's actually just defects and contamination. So this is a picture of the LIGO test mass illuminated in green. And you can see all of this, you can see all of these point scatterers, right? And so every green photon scattered towards the camera is a photon that's been scattered out of the cavity, so that reduces the finesse. So probably for these experiments, it's unlikely that they will have a finesse greater than 10 to the 6 if no other optical cavity can do it. And you do the usual thing if you try to set the cavity's coupling to not be smaller than the internal losses. Yeah. So the other limitation is power. So how much power can you reasonably assume? Can you assume a megawatt, 10 megawatts, 100 megawatts of circulating power? The LIGO experience is that LIGO's currently at 400 kilowatts of arm power, and that has been very difficult. And there are a number of things about LIGO currently at that operating power that are very fragile. And The reason for that is that, again, the coating absorption is very small. It's less than a ppm. But once you have hundreds of kilowatts of power, you're absorbing a fair fraction of a watt. When you do that, the surface of the mirror distorts, and that distortion transfers field from the Gaussian spatial mode into higher order spatial modes. And once you have that, it can behave like a loss. It can mess up control signals. It just is, it's undesirable for the stable and high power operation of an optical cavity. And at a certain point, the more power you try to pump into the cavity, essentially all the power just starts going into higher order modes, and the amount of 0, or fundamental mode content doesn't actually increase. So LIGO has been sort of year by year installing more and more sophisticated thermal compensation systems to try to undo this aberration, or at least compensate for it. So we started with just this barrel irradiator on the test mass, this ring heater, this resistive ring heater. We're now adding a front surface irradiator that sort of in a fairly fine-tuned way is trying to heat the front surface to compensate for the local heating of the beam. And we're installing a thermal transient suppression laser because the thermal timescales involved can be like 12 hours because glass is such a poor conductor. The point is, in picking an operating power for a dark matter experiment, for optical cavity experiment, you have to take all this into account. And there has to be some sort of realism about how much power you can actually tolerate before your thermal compensation system just can't compensate anymore. The other kind of power-based instability is interaction of the optical mode with the internal bulk modes of the test masses. It's called parametric instability. Basically, the internal modes of the test masses will scatter into higher order optical modes, which then circulate inside the cavity and through radiation pressure, drive the bulk modes of the test mass again, the acoustic modes. If you don't control those, they not only they extract power from the cavity, but they saturate the sensors, saturate the control system. The LIGO solution for this has been to very carefully engineer these little acoustic mode dampers, which are glued onto the test mass very carefully. And they're very carefully tuned for certain acoustic mode frequencies. And what these do is that when a parametric instability rings up, this little acoustic mode damper, which has this resistive element, extracts energy from the mode. So you never get positive feedback. So the mode actually never fully rings up. So that's fine, but it's a very kind of whack-a-mole kind of process of figuring out which modes are a problem, making these dampers for it, and then you have to install them in such a way that they're lossy for the bulk modes that you want to damp, but they can't be lossy for the bulk modes that significantly contribute to the test mass motion, because that gives you an extra thermal noise. So that. Sorry?
This picture,
Yeah.
so the yellow is pretty. Or yellow.
Yeah, I didn't explain it very well. So there is this base, this glass base, which is glued onto the test mass. And then on top of the base, there is a piezoelectric element to transduce mechanical motion into a current. And the current is then sent through a resistor, and that's what provides the damping. So there's an instability, there's a power limit from this kind of instability. As I hinted at before, there are angular problems with the test masses that are suspended. You get optical torques. The torsional stiffness, the spring constant, just has this basic scaling of length times the pump power divided by C. One is a positive sign, one is a negative sign. So if you crank up the power high enough, eventually what happens is the angular dynamics of the test mass become totally dominated by radiation pressure or radiation torque. And because one of these has a negative sign, one of them is dynamically unstable. So you just have to have active feedback to correct the angular motion. And as soon as you have active feedback, you have control noise. So it then becomes a question of, are you really going to have, so if you have a control system that has to operate at say a few hertz, is that really compatible with shot resistant operation at a few hertz? It's a little bit difficult to say. So overall, if you ask me, sort of what's a reasonable optical cavity power to assume in sort of a futuristic but realistic sense, I would pick a few megawatts. So the LIGO target for the next 5 or 10 years is 1.5 megawatts, for instance. Squeezed light. Right, so squeezed light obviously has been used in LIGO, used in Haystack. The implementations are a little bit different and the overall strategy is a little bit different. But this is it's a way that you can reduce the shot noise limit, obviously. It's possible to generate about 20 dB of squeezed light in the optical. But in terms of actually implementing that in a suspended interferometer, what we get right now is about 6 dB, so a factor of 2 in amplitude. And that's due to spatial mode mismatch. So again, all of these thermal problems in the interferometer, they also reduce the efficacy of squeezing. Getting more squeezing is it's hard. It requires a lot of very fine control of spatial modes. The target for the next 5 to 10 years is 10 dB. So I wouldn't, in projecting sort of what you can do in a dark matter experiment, the polarimetry experiment, I wouldn't go assuming 20, 40, 50 dB. That's not going to happen. 10 dB is a already ambitious goal. Obviously, another thing that has been thought about here, and it sounds like is actually going on here, is to switch from a homodyne readout or switch from a continuous readout to photon counting. And there is this breakpoint if you depending on what mass you're looking for for the ALP, and also how much squeezing you might have and how much dark count rate you have in a single photon detector, there is a breakpoint at which you should switch over from squeezed homodyne to single photon readout. And if you say you're looking for a pico EV ALP and you have a 6 dB squeezer, if you can get an SNSPD with a dark count rate below 10 to the minus 4 hertz, you should switch over. There are then some integration challenges, like how do you separate the signal photons from the pump photons, but it's a whole other discussion. Just in general, I've been hinting at this, but doing interferometry below 10 hertz on the ground anyway with suspended optics is hard. LIGO only claims to go down to 10 hertz. We don't claim to ever try to provide observational data below 10 hertz because it's just too noisy. There's control noise, there's all sorts of technical noises. You have to have a feedback control system. These thermal noises get worse at low frequencies. So again, for a dark matter polarimetry experiment, I personally would be looking, if it is sort of a ground-based suspended interferometer, I would be looking at coffee frequencies above 10 hertz, or at least above a few hertz if you want to add some features in. So where does that add up? This ends up in, this is my personal set of projections for how I think optical polarimetry for ALP searches could be scaled up in the future. So first of all, the different colors are a 10-meter apparatus, a 100-meter apparatus, a 1,000-meter apparatus with sort of increasing amounts of cavity power and increasing amounts of squeezing. The solid lines are the shot noise curves only. These dashed lines sort of coming off of each curve are what happens if I add in a rough estimate of where I think the Brownian noise might be. Also given a certain amount of futurism for coatings. So again, if you cut off at a few hertz of observation, that means that you're cutting off in mass range at 10 to the minus 14 V, something like that. And then you can sort of see that the effect of the coating Brownian noise is to give you this flattening out of the G again that you can probe. So I'm not the only person who makes these projections. There is this paper on the so-called dark geo concept. And there are also some projections for dance. The dark geo concept comes from the LIDA people. So I don't think I have conclusions, I have questions. I have questions for where this sort of polarimetry stuff is going to go in the future. So should we be doing narrowband searches? Should we be doing scan searches? I think that has to be gamed out, sort of looking at the technical noise and the thermal noise in a bit of detail. There's implications for the birefringence control. If you want to make long baseline kilometer cavities, where do you put them? Are you going to go through the expense of sort of building a whole new facility, or would you repurpose something? How how is this complementary with other searches that are going on in the same mass range? So DM radio, superconducting RF cavities. Again, what's the complementarity of superradiance? How firm are the superradiance bounds such that you should say, I'm going to stop. I'm going to not probe any deeper than a certain gamma in a certain mass range. And then there's sort of a more general, like an unknown kind of question, sort of beyond sort of these quantum and thermal noises, beyond scattered light, beyond controls, beyond thermal control. Are there any sort of polarimetry specific concerns that are being missed and should be considered for these cavities? Is it?
Yeah, I'm here just on the previous slide, I guess. So is this always in out territory or what is it you see that?
Yeah, like it's just up above the upper limit of the plot. Sorry, it goes up to 10 to the minus 7.
Like awesome.
Oh, sorry, where's the benchmark models?
Yeah,
Let me put that in. Let's see, 10 to the minus 7.
like does your green line get close or?
I didn't put the two on the same plot. Let's see, 10 to the minus 7 gets you. Yeah, it's sort of between 10 to the minus 17, maybe 10 to the minus 17 and 10 to the minus 7. So it's sort of all the way down here. So yeah, I think in terms of the sort of the abstract physical motivation, I think it has to be really for ALPS excluding the QCD axion is probably the right way to think about it. That's sort of what you'd be looking for. Yeah.
Related question in terms of scaling, is there, what does a sort of large cutting edge superconducting microwave cavity? That just is not, doesn't compete somehow, because as you say, you can get very high powers, very high Qs at high powers.
Yeah.
Accelerator, and then
I don't know how to evaluate. So in the SNOMAS report, there are projections for SRF cavities. And they have these 3 different regimes of, like, today's technology, improved technology, and then what they call futuristic technology, which gets all the way down to the benchmark models. I don't know how to evaluate the realism of that. I know that they can have very high Q factors. I don't know about the power handling. Yeah.
Can you like slide 8? I have a question about the bulk material, or I think more. Otherwise, stop there. Yeah, so I might just not be understanding it correctly, and this is like very naive. So we're talking about the current status of the silicon sample stacks for LIGO, which has a Q factor of 10 to the 4. How thick is like are those stacks, I guess, like, and then or like could you push the limit of the bulk silicon thickness to be thicker so that you're like maybe you're sacrificing the thickness of it, but then you're improving your Q factor? Like, would that be a sacrifice that's worth looking into maybe?
Yeah, so yes, every possible permutation of silica and tantalum is currently being tried by somebody somewhere. So they are trying exactly more silica, less tantalum. They're trying nano layers where you go sort of nanometer by nanometer and interleave different things. They're trying zirconia, niobium. Germania has been pretty promising, but the answer is yes. It's the right way to think about it. How do you engineer the stack? How do you engineer the details of the stack to try to weight different materials while still getting a higher fertility?
What's the, I guess, the upper limit of the thickness of the stack that you could potentially work with then?
That's an interesting question. My understanding is that one limit that you run into is when coatings are deposited, they typically produce a large amount of stress on the optic. So eventually, if you deposit a coating that is too thick, you distort the figure of the optic. Yeah.
Wondering, most axion circuit and out circuits have sensitivity to dark photons and other kind of wavelengths that matter. Is that true of this approach as well, or is it something about the polarization of the dark photon?
No, so it is generically in interferometers. Let's think of Michelson interferometers. Yeah, so generically, when you have suspended masses, dark photons should produce acceleration of the masses. And as long as you are sensitive enough that you can sense the gradient of the dark photon field across the baseline of the cavity, so that you get some amount of differential motion between the test masses, you should then see a signal. And there are limits from LIGO on that.
Okay, thanks very much. Please thank the speaker.